All right, let's get right into this explainer on synchronous machines. Look, if you're a grad electrical engineer stepping into the offshore industry, you already know the stakes out there are absolutely massive. This whole explainer is designed specifically to bridge that gap between your classroom theory and the intense, high-stakes reality of offshore engineering. We're going to break down exactly what happens inside those massive generators powering the rigs, and we'll translate all that complex physics into practical things you actually need to know on the job.
And honestly, the most crucial point to grasp right out of the gate is this. Understanding the fundamental physics of this tiny air gap is absolutely essential. Every single watt of electricity on your offshore platform, literally everything keeping the lights on and the drills turning, starts right here. It all comes from this invisible magnetic field bridging a spinning rotor and a stationary stator. If you don't fundamentally understand how this gap behaves under stress, well, you just can't effectively protect your platform's power grid.
So, here's our roadmap for today. We'll start with the offshore power heart, then look at the frequency formula, dive into armature reaction dynamics, map out the timeline of a fault, and finally finish up with reading phasor diagrams. Let's jump in.
Part 1. The offshore power heart. Let's look at the physical components.
Think about the physical relationship we're looking at here. You've got the spinning field winding right there on the rotor, and then wrapped around that are the stationary three-phase windings of the stator. So the rotor carries your DC excitation field winding, right? And it rotates its shaft speed to set up the main magnetic flux. Meanwhile, sitting totally still, the stator carries your three-phase AC winding. The entire operation of your offshore power grid relies entirely on this magnetic interaction constantly sweeping between these two physical structures.
Moving right along to Part 2, the frequency formula and steady-state operation.
Okay, this foundational formula right here defines the absolute heartbeat of your platform. It links the mechanical speed of your prime mover, say a gas or steam turbine, directly to your electrical frequency. F equals P times N divided by 120. It's a beautifully simple, unyielding equation that perfectly marries the mechanical and electrical domains.
And putting that formula to work brilliantly illustrates how different rotor constructions just have to spin at strictly different speeds to maintain that vital 50 Hz grid we need. For instance, a salient four-pole machine, which you'd often use for slower prime movers, has to spin at 1,500 RPM. But if you have a cylindrical two-pole generator, which is typically driven by high-speed turbines, that thing needs to spin at a blistering 3,000 RPM just to yield that exact same 50 Hz result. The physical design of the machine fundamentally dictates its operational speed limits.
All right, Part 3, armature reaction dynamics.
So what actually happens the moment you close the circuit on a load? Well, a steady-state current starts flowing in the stator coils, and this stator current creates its own flux that actively opposes the main field flux coming from the rotor. We call this the armature reaction. The magnetic action taking place is literally a tangential pulling between the stator and the rotor. It is highly analogous to stretching a physical spring. The greater your electrical power demand, the harder that magnetic pull becomes, and the further you stretch that invisible magnetic spring across the air gap.
Which brings us to Part 4, the timeline of a fault and our reactance phases. Now, this timeline tracks the chaotic, and let's be honest, potentially destructive sequence of a fault event. When a short circuit hits, your stator flux rapidly spikes and aggressively tries to penetrate the rotor poles. This forces the machine through three very distinct reactance phases. First, you get the subtransient phase, in those very first few milliseconds. Then it moves into the transient phase, lasting up to about 3 seconds. And finally, if it's still going, it settles into the steady-state synchronous reactance phase.
Tying those phases to our math, you've got to make sure you're picking the right tool for the job. If you are calculating maximum fault breaking currents to size your switchgear, you absolutely must use the subtransient value, XD double prime. It's a very low value, which means you're dealing with extremely high fault currents. If you're analyzing system stability over a couple of seconds, you shift to the transient reactance, XD prime. And for your everyday steady-state load flow calculations, you just use the synchronous reactance, XT. I can't stress this enough. Using the wrong value for the wrong time frame will lead to catastrophic engineering miscalculations out there.
Let's zoom in on those first few critical milliseconds for a second. Why is that subtransient reactance so incredibly low? It's because it's dominated by a parallel combination. You have the field leakage reactance, XF, and crucially the damper bar circuits, XKD. The math works out to XA plus the parallel product of XF and XKD. These damper bars are actually embedded right in the rotor specifically to repel sudden flux changes. They act almost like a squirrel cage in an induction motor, forcing the fault flux into high-reluctance air paths, which creates that massive, instantaneous current spike.
Finally, let's wrap up with Part 5, Reading Phasor Diagrams.
Let's bring the math and the physics together so you can map out exactly what is happening inside the machine. It's a simple step-by-step. First, you start by drawing your reference terminal voltage. Then, you draw your armature current, making sure to account for its power factor lag. Next up, you add the perpendicular voltage drop that's caused by the synchronous reactance. When you connect your origin to that final point, boom, you've constructed the internal EMF of the machine. And that angle right there between your terminal voltage and that internal EMF, that is your load angle, delta.
And this load angle, delta, represents that exact stretched spring we talked about earlier. It is a direct, real-time visual indicator of your generator's mechanical and electrical stress. When you're at no load, the spring is totally relaxed, so delta is basically zero. But as you load up the generator, that angle physically widens, usually sitting pretty comfortably around 30 degrees when you're at full, continuous offshore load.
But here is the critical operational reality, the thing that should keep you up at night. If a major fault or a massive sudden load swing yanks that load angle past 90 degrees, your magnetic spring just snaps. You suffer a total, catastrophic loss of synchronism, risking severe damage to the prime mover and a complete blackout of your offshore platform. Understanding all of this leaves us with one incredibly important question for your everyday offshore operations. Are you truly watching your dials?